I will introduce our recent work in developing a statistical finite element method and its application in creating a physics-informed digital twin. My collaborators are Girolami and Febrianto. Today, most engineering products are designed using finite element models, and these models are inherently misspecified like any other model. They are misspecified because of lack of operational data and uncertainties in geometry, material, loading, and so on. Nowadays, the uncertainties are considered through codified safety factors, which of course may lead to very inefficient structures. Fortunately, we have more and more monitoring data coming from engineering systems in operation. We can use this data to improve our finite element models. In our context, we deal mostly with strain data, which comes, for instance, from digital image correlation, fiber optic sensing, or satellite remote sensing. The overall objective of our research is to develop a statistical framework which enables us to synthesize measurement data with finite element predictions. We have given a real system, such as the bridge shown here, a conventional finite element model like used nowadays. We have data coming in from a real system, and we would like to synthesize the data and the finite element model predictions in order to infer the real system performance. We have here several challenges. First, as mentioned, finite element models are misspecified, so we have to take this into account. In addition to that, data is usually scarce in engineering in comparison to a machine learning context, for instance. We decided to use a Bayesian modeling approach for our statistical framework. This means all uncertainties are represented as probabilities with corresponding probability density functions. We have a probability density function for the finite element solution U. We have data Y with corresponding noise E. We combine both in order to obtain the real system response Z. This is the outline of my presentation. First, I will introduce our assumed statistical data generating model. Then the respective prior probability densities for the finite element solution and the model reality mismatch. The prior probability densities will be combined with a data likelihood to yield the posterior probability density for the finite element solution and the true system response. Finally, I will show two examples. First, an illustrative one-dimensional verification example, and subsequently an operational railway bridge. First, our assumed data generating model. The data vector Y, which may contain the measured displacements or strains, is decomposed into three components: a finite element component U, a mismatch component D, and a measurement noise component E. In this equation, we have also a matrix P, which projects a finite element solution to a sensor space, and a scalar parameter rho. The first two terms, rho PU plus D, are equal to Z, which is the true system response. We assume that each of the random vectors U, D, and E are independent and are normally distributed with respective mean vectors and covariance matrices. In a Bayesian context, we need now their prior densities. The prior density of a finite element solution is obtained by solving a conventional probabilistic forward problem. I have included here a Poisson-Dirichlet problem, which may describe heat diffusion. In this stochastic partial differential equation, the diffusivity kappa and loading F are random. After discretization with finite elements, we obtain an algebraic system of equations. A is here the stiffness matrix. By solving this equation, we obtain a probability density for U, which we approximate as a normal distribution. Next, we need a prior for a model mismatch. We don't know much about the model mismatch. Therefore, we assume a squared exponential kernel with an unknown two hyperparameters sigma and L. We use this kernel to determine the covariance matrix of a mismatch vector D. We can now compute the posterior finite element density by combining the observation data and the mentioned prior densities. The prior density for a finite element solution is obtained, as mentioned, by solving a probabilistic forward problem. The data likelihood is given by our assumed statistical model and the measurement data. We can compute using a Bayes formula the posterior density of finite element solution conditioned on a measurement y and the hyperparameters. We obtain point estimates for the hyperparameters by maximizing the marginal likelihood. After we introduce this point estimates in a posterior finite element density, we obtain our final expression for a posterior, which is a normal distribution with explicit or closed form expressions for a mean and the covariance. I would like now to introduce two examples to demonstrate the application of a proposed statistical finite element method. The first example is a one-dimensional Poisson-Dirichlet problem with random forcing. Forcing is here a Gaussian process and has a form given here. On the right, you can see the finite element solution. The horizontal axis is the domain, the vertical axis is the solution U. In blue is the mean of a finite element solution, and in light blue, it's 95% confidence region. I've included in this plot also an assumed true system density in black. We want now to infer this true system density from a limited number of sensors and readings. In each of the four plots, I have different number of sensors and repeated readings. In addition to that, I have included in each of the four plots the true finite element density from a previous page. On the top left, we have four sensors and one reading from each. And in black, you can see again the inferred true system density. The confidence region is very large. We can narrow it down by just making repeated readings from available 4 sensors. So if we have 100 readings from each, this confidence region becomes narrower. If we increase the number of sensors and the readings, like here, right bottom, you can see that this inferred density in black becomes very close to our original assumed density for the true system. My next example is an operational railway bridge which is located along the UK West Coast Main Line. This bridge has been instrumented by our colleagues in Cambridge with a monitoring system for measuring strains. The bridge superstructure consists of 2 main I-beams connected by 21 transverse I-beams, which are hidden in this finite element mesh below the deck. When a train passes this bridge on the left track, this leads to the shown displacements, which are of course magnified. The displacement will lead in turn to strains. In the following pages, we will focus on the strains in the main left I-beam. First, a comparison between a finite element and measured strains at the midspan of a left I-beam. Here you can see the strain plotted over time, somewhere at the midspan of a left I-beam. At the top is the upper flange strain, at the bottom is the lower flange strain. The plus signs indicate the measured strains, and the red line the computed finite element strain. We will focus now on the strains at time 1 second, 2 seconds, and 3 seconds, with the corresponding deflected bridge shapes shown on the right. So we look at the flange strains along the left I-beam. In these 3 plots, I have plotted the strains. In blue are the upper flange strains, and in red the lower flange strains. In addition to that, we have the plus signs, which are measurement from 40 strain sensors. In black, I have plotted the inferred true flange strains and their corresponding 95 confidence regions. We can see in these 3 plots that the inferred true strains lie between the measured strains and away from the prior finite element strains. Next, we want to study if we can infer this response also with a reduced number of sensors. So the first top 3 plots are the same like on the previous page, and the bottom 3 plots use only 10 measurement points. You can see here that the inferred true strains in black are in very good agreement with the inferred true strains with 40 measurements. So this means that we can have only few measurements in order to infer the true strains. As you saw, the statistical finite element method gives us a possibility to synthesize observation and simulation data. In our approach, we take into account all uncertainties in the data, model parameters, geometry, material, and so on. As you saw in the last example, a limited amount of data is sufficient to infer the true system response, and we believe this makes the statistical finite element method ideal as a principled means for creating physics-informed digital twins.